Okay, so let's get started. It's 2:30. Yeah, so how was the quiz or midterm? Okay. Yeah, sorry, the classroom is a bit cramped. I didn't realize it, only after the fact. Next time I'll book a much bigger classroom. Yeah, so it's going to take us a few more days to finish grading. And then after that, yeah, we'll release the scores. Yeah, at the end of the day, like the quiz is curved, so in the sense that roughly the distribution will match whatever it was in the past year. So yeah, it wasn't supposed to be too hard, but then finished grading one problem and then it was like really bad. So yeah. Anyways, I mean it's fine. I mean everybody, we're all in the same boat. And there's also like the other tests left, and then the final, right? And then so that's like a lot of the weight, and also the homework, right? Okay, so but like in some sense, yeah, it's also not too bad if you don't do so well in this class, right? I mean, this is just like one small part of computer science, Doesn't say if you're a bad software engineer or whatever, just one small part of computer science. Okay. Okay, so now let's get started. So now we're done with like dynamic programming. Sort of the next part. Hey, I would really appreciate it if you didn't talk. Like, if you want to talk, just please do it outside. So the next part of the class will be on graphs. Okay, so now we're like done with dynamic programming. Now there'll be a whole month or so of graphs. And you probably have seen, breadth first search and depth first search, but we'll redo them again, and then kind of, there'll be sort of the first blocks towards more and more complicated things that we can do, okay, on graphs. Okay, so what's a graph, right? You just have some nodes and some edges. The edges may have like the directions, right? Or they may not, and the edges may also have weights, okay? So in this class, we'll consider like all types of graphs. But for this particular class, okay, like for this particular lecture, the graphs will have, the edges can be undirected or directed, but they'll have weight 1, okay? So you can think of them as you can think of them as unweighted graphs, okay? But just for this particular class, and then in future classes, we'll make the graphs weighted and so on, okay? Yeah, I mean, I'm sure you've all seen graphs before. So here's like some bunch of definitions, but basically, right, what is a graph? You have some nodes, you have some edges. We're gonna, in this class, we're gonna say n is the number of nodes and m is the number of edges. Between every pair, we'll just have one edge, okay? Or two edges if one is going this way and the other is going that way. Well, like we won't have parallel edges. Yeah, and then for this lecture only, the graphs are unweighted, right? If there's n nodes, right, then there can only be up to O of n squared, number of edges, right, between every pair. All right. Okay. Any questions about graphs? Okay. So yeah, sort of like the next few lectures will be on ways to search within graphs, okay? Or like explore graphs. So for this particular lecture, what we want is we're at some node S, and we want to like explore the graph with the perspective of S, okay? So that's going to be like the main node, and somehow we want to find all the nodes that are reachable from S, or all the distances from S to all the other nodes, okay? So one way to think is like like you have a map, and then all the roads are the same length, right? Maybe they're all like 1 mile long, and you want to figure out all the distances from, let's say, from a particular place, like the library to all the other restaurants, for example, okay? And in general, like one nice thing about graphs is like they can model many like things. It's not just a graph. For instance, in the web, at least like the first first few algorithms to index the web. Essentially, how they worked was every web page was a node, and if they had links, that were you know, like basically if one web page referenced another, that was a link. And then sort of at least the first few algorithms to rank web pages. So if you search like, oh, you know, the restaurants that are around me, right, and you get a bunch of results, how like Google and the first companies, how they made this list is essentially like which node has the most number of links coming to it, okay? But yeah, like route planning in maps, solving games, that's also another example. But just think like graphs are a general tool to model like relationship between objects, so they're very powerful, okay? All right, so now let's talk about how graphs are stored. So there are two main ways that graphs are stored, okay? One is like this, okay? So basically I have an n by n table, and I put a 1 if there is an edge there, okay? All right, so for instance here, right, there's an edge from w to x, so there's an 1 here, but there's no edge from x to w, right? This is a directed edge. So you know that's a 0 there. You know, if the edges didn't have orientation, you could go both ways. Then you know then there'll be a wx at 1, and then also xw would have a 1, right? All right, so that's one of the ways, okay? And then the other way, okay, so this is called, well, we'll see later, but the other way is more for like better for sparse graphs, which is essentially for every node, you just keep a list of all its neighbors, okay? So for instance, let's say node 1, right, it has neighbors 2 and 3, 2 has neighbors 3 and 1, and so on, okay? Right, so the first one was called adjacency matrix, and essentially what this, you know, if you store your graph like that, what it allows you to do is it allows you to quickly check if one edge is there, okay? But it uses n-square space, right? Because you have to store like a 0 or 1 for every potential edge that could exist. And the other thing is this list, right? Basically, it's a very, very like concise representation. But to check if there's an edge, right, you really have to spend a lot of time. Like if you want to check, you know, is there an edge from vertex 1 to vertex 10? What you do is you go to like the list, you know, vertex 1's list, and you walk down the list until you see vertex 10, okay? Yeah, like I said, you know, adjacency matrix, right? Use for every possible choice of an edge, you just have a 1 or a 0, whether that edge exists or not. You know, it takes n-square space, and you know, it's fast for some things, but not fast for the other things. You know, checking for an edge takes one time, but you know, for example, finding all the neighbors of a vertex takes takes up to n time, even if the vertex has, let's say, no neighbors. Okay. And then the other thing is like this list, right? This list is a very concise representation, and the reason is, you know, every edge is only stored twice, right? Considering edge from 1 to 2, right? It's stored in 1's list and also 2's list, and we never store any edges that are not there, right? We only store edges that are there. And you know, the advantage of this is like if your graph has very few edges, then you're only storing the edges essentially. So you're not storing a bunch of zeros. So that's space efficient, I guess. But also, if I want to find all the neighbors of a vertex, then it's just in the list, right? I've already stored the neighbors. So that's very fast. But checking if a particular edge exists in the graph is slow, okay? In this class, we'll mostly be talking about this representation, adjacency list. Essentially, what you can imagine, right? I mean, the details don't matter, but essentially, when we talk about, you know, when we access graphs, just think, for every node, right, I know all the neighbors of the node, because it's stored in this adjacency list, okay? All right. Any questions so far? Okay, so now the next thing we're going to do, right, this may be like, you know, I'm sure like one of the intro CS classes has talked about this, but now we're going to talk about like this fundamental operation on a graph, okay? It's called breadth first search. And, you know, I mean, there's a bunch of words, but like intuitively what's going on is I'm going to give you a starting point, right, S, called the source, let's say. And I want to figure out all the, you know, basically for every other node in the graph, how can I go from the source to all the other nodes, okay? So that's essentially what breadth first search is going to allow us to do. And essentially what this does is, right, if I have a source, it allows me to partition the rest of the graph into layers, okay? And essentially layer I will be all the vertices that are at distance I from the source, okay? So right, the first level will just have the source, you know, the 0th level. The first level is all the neighbors. The second level, is all the neighbors of the neighbors that were not neighbors. The third is neighbors of the neighbors of the neighbors that were not previously seen, and so on, okay? So I'll have a diagram. But essentially what this does, it kind of layers the graph into many layers. And sort of the ith layer is, you know, all the vertices that are I hops away from the source, okay? So it's kind of like this, okay? Yeah, you know, like you have the source, and you kind of want to partition the rest of the graph into a bunch of layers. And sort of in, you know, layer 2 is, or level 2 is, all the nodes that are sort of 2 hops away from the source, okay? That's essentially what breadth first search allows us to do. And then it's really easy to say, okay, what is the distance, right, from the source to this node? Well, just check what layer it is in, right? That's exactly the distance. That's exactly how many hops it takes to go from the source to that layer, okay? So now, I mean, I'll tell you how to construct this representation, but at a high level, does it make sense? Like, what we're trying to do? We're trying to partition the graph into like sort of layers, where the ith layer is all the nodes that are at distance I from the source, okay? So, you know, one caveat is, let's say, you know, for this node, right, there are multiple ways to get there. But essentially, the first time we get there is like the layer that's part of, okay? Because, right, let's say, you know, I have my neighbor, I'm a source, I have a neighbor vertex. That neighbor should be in layer 1. But of course, it could be possible that it's, you know, I can go to that neighbor using a path of distance 10, right? But I don't want that. I want the fastest way to get there, okay? And sort of this diagram like naturally tells us how to do BFS. Essentially, what we do is we're at some like frontier, okay? You know, we have explored this part of the graph, and we still have the rest to explore. What we do is we say, okay, what are the neighbors of all the vertices at this level that have not been seen yet? And that defines the next level, right? So that's essentially what BFS is doing. It's sort of exploring the graph in waves, you know. And the next wave we say, okay, what are the neighbors of all the vertices that are currently in the, that are in the current wave? Okay. So here's another diagram. So let's just say this is a graph, right? All the edges, you can go both ways. S is our source, right? So S is our current, frontier. And then we say, okay, what are all the neighbors of S? Well, I have A and X, right? That's the next one. And then you say, okay, now I'm at A and X, right? That's the next frontier. How do I push one more level, right? So I say, okay, what are all the neighbors of A and X? Well, that's Z, D, and C, right? Okay, and then they say, okay, what about, now I still have some vertices that have not been visited. Then you say, okay, what's the next frontier that I can push? F and B. Okay, so, and you might notice, like I said before, while you're doing this, you may see the same vertex many, many times, but you say, okay, as long as I've already visited that vertex before, I don't go to it again, right? So let's say I've already reached a vertex X in the level 1, right? It's 1 hop away from S. And then I go to the level 2, right, at D. And of course, there's an edge from D to X, right? But I don't want to go to, when I'm at D, C, and Z, right, the level 2, I don't want to go back to X because I've already seen it, right? It's already part of a previous like layer, right? So essentially, I only push on the vertices that I haven't seen before. Okay. So I'll have the code up shortly, but like internally, does it make sense? Like I'm just pushing one more layer at a time. And essentially, I never visit things I've already visited. So I'm only visiting like unique neighbors at every time. Okay. Anything? Any comments? Questions? Okay. So it looks kind of painful, right? But that's why I showed it at the end. But I mean, let me break it down. Okay. So essentially, right? Let me break it down. I mean, it's not saying anything like too interesting, right? It's just saying, okay, initially I'm at this node, and I have an active like frontier. Okay. Initially, the frontier is just my node. Okay. So what do I do, right? I say, okay, for every vertex in the frontier, right? I go to the neighbors, okay? I go to their neighbors. If that neighbor has not been visited before, right? That means, oh, it's a new vertex I can explore. Then I add it to the next frontier, right? And I say, okay, the level of that is I, right? It's the next frontier. And then I keep doing this, right, until the frontier is no more, until I've explored everything. Okay? Right, so like the main thing is, right, you have to check, right? Every time you encounter a vertex, you have to check, have I seen this vertex before? So what you do is you just keep track of, let's say, a dictionary of saying, okay, for every vertex, what is the wave of that vertex, or like the, what level is that vertex part of? And so every time I encounter a vertex, I just make sure I've never seen it before. Okay, so if I've already seen it before, right, I don't add it to the frontier, because I've already seen it before, okay? Yeah, any questions? Yeah, just think like, okay, your perspective, okay, you're walking on a graph, right? Like you're at a you're at a node and you see like all the nodes that are there, right? The next step, and you take one more step forward, and then you take one more step forward, and so on. You just have to make sure that you're only going to like unique nodes. Okay? Yeah, any comments? Like, yeah, I mean, just just have this like picture in your mind, right? Start at some node, go to the neighbors, go to the neighbors of the neighbors, neighbors of the neighbors and neighbors, and so on. Okay? All right. Yeah, so how fast is this, how long does this whole process take? Any thoughts? Right, I'm just walking on this graph, right? I'm going level by level. So the key is, right, I'll only walk on an edge at most one time, or at most constant number of times, right? Maybe only one time, I think, yeah. I'll only walk on an edge at most one time, right? Like I'm never, when I go from S to its neighbors, right, essentially I'm like walking this way and I'm walking this way. I will never walk this edge ever again, okay? So what that means is when you're running the code, or when you're running this the algorithm, every edge will only be touched once, okay? And every node will only be looked at most twice, okay? Or sorry, every node will only be looked at by its edges, right? So essentially, the whole running time of this algorithm is proportional to the number of edges that you have, okay? Right, like, okay, so why would, so I go from here and then here, right? And I say, okay, I may want to consider this edge again, but no, like I've already visited this. So then I never go back here, right? So it's like every edge is only walked on at most twice. Okay. Okay. Does that make sense? Like, why every edge is only like touched, I'd say, at most twice. Okay. And essentially, okay, I guess this is the same thing, right? Imagine running this on the adjacency list. And you can see that like sort of the adjacency list of a vertex, right? When I expand its neighborhood, right, I only go to that vertex once, right? I only expand the neighborhood once. If I have to do it again, I say, oh no, I've already visited that vertex. I don't do it, right? So that means I only expand the neighborhood of that vertex once. So essentially, I only loop over the neighbors of a vertex one time. Okay? So that means the total running time is the number of edges, proportional number of edges in the graph. Okay? Yeah, so the total running time is essentially big O of m. I have a n here as well. And this is kind of for an edge case, right? So when you run BFS, like if there are nodes that don't have any edges, they're isolated. Technically, like one way to say BFS is you also visit, you also kind of check that there are any isolated nodes. So if your graph is empty, right, you still have to spend n time to kind of check they're empty. But essentially that part doesn't matter. Essentially, the main running time is O of m. And in general, like most of the graphs in this class, there'll be, m will be at least n, right? Because the graph it won't have any isolated nodes, okay? All right, so this is considered like fast for graphs. And the reason is you're essentially doing sort of like one work per edge, okay? Okay, so you're essentially doing work that is as large as the size of the input itself. Okay, so it's not like you're spending so much time going back and forth on an edge. All right? Yeah, any comments? Questions? Okay. Yeah, so why is this, why do we want to do this? Well, it actually solves a very interesting problem, okay, doing this. It essentially says, okay, if I start from the source, it gives me the fastest way to get to all the other nodes in the graph, okay? And essentially, sort of this, let me go back to this diagram, sort of the level of the vertex will be how many hops away is it from the source, okay? So that means it's like the fastest way to go from the source to that level, right? So essentially saying, the fastest way to go from S to V takes 3 steps. That's what this is saying, okay? And how would you reconstruct the path itself? Well, in the BFS, right, when you're exploring a vertex, you just remember parent pointers. You say, okay, how did I go to that vertex? Well, I came from this vertex. So you just draw an edge, okay? What that means is if you keep track of how the vertices are being explored in BFS, this will make something called a tree, shortest path tree. Essentially, the source will be at the root, and all the other vertices will be leaves, will be at intermediate nodes in the tree. And by following the edges, that gives you the fastest way to go from the source to all the other nodes, okay? And like I said, how do we construct this tree? Well, we just remember how we got to that vertex, okay? So for instance, let me just go here, right? So how do we go to vertex A and X? Well, we came from the source. So in the tree, right, we keep this edge and this edge. How do we go to vertex Z? Well, we came from A, so we keep this edge. How do we go to D? Well, we came from X, okay? And so on. We wouldn't keep this edge, because BFS never hit this edge, okay? So essentially, we just keep all the edges that BFS actually, went to, and that will make a tree. And essentially, that tree just keep tracks of, for every node, which wave or which level is the, are the vertices at, okay? All right. Does that, is that okay? Comments? Yeah, so I would actually if you go home and try to implement BFS by yourself, it's a very instructive exercise, okay? All right, so why? Can anyone tell me why BFS will reconstruct the fastest way to go from a source to some node? So I'm just claiming that it will give you the fastest way, but why is that? So let's imagine. Yeah, sorry. Go ahead.
I guess because the way that you go through each level, the first time you ever encounter any node is going to be at the lowest level it can. So it can't. So it showed up earlier, it can't show up later.
Yeah, exactly right. So it's kind of almost proof by the way the algorithm is, but if you want to be a little formal, it's by induction, right? So what we say is, we'll say by induction that BFS finds all the nodes that are at distance 5, right? Let's assume that by induction. Now, how does it find nodes that are at distance 6 away? Well, nodes that are at distance 6 away have neighbors that are at nodes 5 away, right? So then when I explore the neighborhood of nodes that are 5 away, I will find all the nodes that are distance 6 away, right? So that's all I'm saying, right? Like nodes that are at k hops away have neighbors that are nodes at k minus 1 hops away. I've already found those, and then BFS just takes one more step forward, right? So essentially, right, it's just proof by the induction, right? I'm doing it one layer at a time. Okay. Yeah. So if your graph is like unweighted, then BFS is a very nice way to find all the from a source node all the ways to get to all the other nodes. Okay. Yeah. Any comments? Like, did the proof make sense, or like the reason? Yeah, and like feel free to ask me questions. It's better to ask questions now than in a test, right? Then you don't have anyone to ask. Okay. But yeah, so in some sense, right? If you have an unweighted graph, like BFS is the best way to explore it. Okay. Yeah. Any questions finally before we go on to something new? Anything about BFS, like why it works, how it works, running time? Okay. All right. So BFS is really nice for like finding shortest paths on unweighted graphs. But now we're going to explore a completely different type of search. Okay. And this has like nothing to do with paths or how to get there efficiently, but it has some other nice properties, okay, that are also really useful. Okay. Okay. So this one is called depth first search, and DFS will not find you the fastest way to go from a source to the nodes. Okay. But essentially, right. So what was BFS doing? It was kind of doing a very like fair way to partition the graph, right? It was saying, okay, I'm at this level, where are all the vertices at the next level, and so on. DFS is kind of the other extreme. I'm going to go deep. Okay. So essentially, I'm going to try to explore a path as long as I can, right? So BFS was sort of exploring them kind of like one, level by level, but DFS is going to explore just one path very deeply and then come back. Okay. So one way to think is imagine your graph where the edges are walls, right? What DFS is going to do is essentially you're going to like put your right hand on the wall, and you're going to keep walking until you can't. Okay. So essentially, you're going to follow the wall. Okay. Yeah. Another way to think about it is like in DFS, I'm just going to follow one path as long as I can, and then when I no longer can, I'm going to backtrack. And how do I backtrack? Well, let's say along the path that I explored deeply, I left some food, right? So I backtrack along that, and then I keep doing it. Okay. So that's just like the high level, but the main difference is the following. Okay, in BFS, right, we were exploring in like we have this waves, right, frontier, but now we're not going to have waves. We're going to try to go as deep as we can on one vertex. So what that means? So okay, it looks kind of ugly, right? So you don't need right, but essentially, I'll tell you the difference, right? The main difference is, right, when we were defining this like frontier in BFS, right, to go to the next frontier, what we were saying is, okay, all the neighbors. But now what we're going to say is, we're going to say, okay, for a vertex, hop on its neighbors. I don't care about other vertices. Now I'm at this vertex. Now hop on this neighbor, and so on. Like another way to say it is like the way BFS works is you have like a stack or a queue of all the frontier vertices, and you're going to sort of pop from the front. Okay, essentially you're going to say, okay, I'm going to make sure that all the vertices in one frontier are totally explored before I explore the next frontier. In DFS, you're going to pop from the back. Essentially, what that means is I'm going to go as deep as I can to following one path. Okay, so essentially this is what's happening, right? I'm at some vertex. If I haven't visited it before, right, I visit all the neighbors of that vertex. Okay, so that's the difference, right? I'm at some vertex. I visit all the neighbors of that vertex. before it was I'm at some layer, right? I visit all the neighbors of every vertex in that layer. But instead, it's more like I only have this like, I'm very, very narrow-minded, and I only go to one vertex, its neighbors, and so on. So this does it. It's not so like, it's not so clear what's happening. So I'm just going to draw, okay? I'm going to draw on the board kind of what it's doing. Yeah. But the main idea is like you have the stack of vertices that you need to visit, okay? Or like that are your frontier. And BFS is going to pop from the front. DFS is going to pop from the back, okay? So now let me draw this example, okay? So I'm going to draw it kind of big. So I have a vertex A, vertex D, vertex B, vertex E, let's say F also has a loop to itself. Okay, so let's say this is my source. So in BFS, right, what was it like? It was a source, and then the next layer, and then the next layer, and so on. In DFS, it's complete opposite, okay? So I'm at the source, and I say, okay, what is the first neighbor that I can go to? I don't go to all my neighbors. I just go to one neighbor, okay? So in DFS, this is the first edge that you'll take, okay? Right, and then previously in BFS, right, what we did was we popped from the front, meaning, right, then we'll go to the next neighbor. But in DFS, we can say, okay, I'm already here, so I'm going to explore this vertex's neighbor, okay? So then the next edge that I'll take is this, okay? And then the next edge that I'll take is this, okay? All right, so I keep going deep, right? I'm just saying, okay, neighbor of A, neighbor of B, right? This neighbor. And then so how DFS works is, okay, I'm at a current vertex. I just explore its next neighbor, okay? So then the next edge that I try to take is this. But then I notice, oh, B was already visited. So I don't do anything, okay? Okay? And then I backtrack, okay? So I have nowhere else to go. And I keep backtracking. And now I say, okay, now I'm going to go to this edge, finally, okay? All right? Right? Previously in BFS, right, like you'd go to this edge first and then this edge next, right? But here we're going to go deep, right? We explored we went very deep on this path, right? And then we had nowhere to go, and then we backtrack, right? And then finally we went here, right? So if you can imagine, right? So, okay, so essentially for BFS, kind of okay, you can call it a queue or stack or anything, right? Just basically whatever is keeping track of what's happening, right? Essentially, right, it will be A, and then it will be B and D, right? The next generation, and then it'll be E, right? Like you go to A, and then you go to B and D, and then you go to E. But in DFS, right, it's like you go to A, and then B, and then E, and then D, and then finally, you go back to A, okay? It's like, you keep adding neighbors, right? In both BFS and DFS, right? You keep adding neighbors, right? There's a next to visit. But in BFS, you come from the front, right? You say, okay, things that were like added first, I visit them. But in DFS, it's like things that were added last, I visit them first, okay? So that's why I go deep here. And then you can say, okay, in DFS, we can also have it so that it visits all the vertices. So then finally, right, let's say I explore this part. Now what do I do, right? Then I explore this edge, 6, right? Then instead of, BFS would explore this edge, but now I just explore this edge, 7, and then explore this edge, 8, okay? Does that make sense? like I'm going to explore, right? I'm at some node. I'm going to immediately go to the neighbor if I can. That's DFS, okay? Like, just think like you're in a maze, and you're going to just keep following, like, like if you're, one way to solve a maze is you go deep along one path. Yeah. So I mean, yeah, you don't have to, but then we can say, like, just say for DFS, let's just make the convention that, like, you want to visit all the vertices. So essentially what you'll say is, right, while you're running, you'll say, okay, C is like not connected, right? So you can stop there, or we can just say DFS or BFS is such that you have to visit all the vertices at least once. So it's just like a minor the edge case, okay, yeah. Yeah, I mean, just, okay, if it's confusing, just think like this part wasn't here. Okay. Yeah. It's going to be like, for one problem that we're going to see, it's going to be important that you also visited vertices that were not like connected to the source. Well, we're going to see why in a bit. But yeah, like you can also choose to not go to that part of the graph that's not connected to you. So one interesting thing about DFS is the following. Okay. So BFS had this nice application where it helps you find like the fastest way to go from the source to other nodes. DFS does not have that, right? It's like not giving you the fastest way to go from A to D, right? Because it's saying to go from A to D, I go all the way around. Okay, that's not the fastest way, but it has like some other application that's really useful. Okay. So the main use case of DFS, or one of the main, is something called back edge. Okay. So what is a back edge? Back edge is following. Right? So let's say, right, in DFS, right, you started at this node. Oh, that's bad. Okay, you started at this node, right? And then you went here, and then you went here, and then you went here, and then, right, you couldn't go further, so you backtracked, and then you went here. You couldn't go any further, so you backtracked here, right? Okay. But let's say that, there was an edge that was going from this node to here, okay? Okay. So that's called a back edge, okay? So it's like saying, right, right here, right? You're going here, 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 right? Right. So the DFS is sort of, what are the good edges, right? This edge is good. This is exploring something new. This is exploring something new. But like this edge is going backwards to something you've already explored. Okay, so that's called a back edge. Okay, like anytime you encounter an edge, that's pointing to something that you've already seen before. Okay. All right. Yeah, and it's not too hard to figure out which edge is a back edge, and the main idea is, right, while you're running DFS, you keep track of like which nodes haven't been finished yet, and if you ever point to a node that hasn't been finished yet, then that's a back edge. The reason back edges are useful, as we'll see, is anytime there's a back edge, there is a cycle in your graph. Okay, so back edges help you find cycles in your graph very, very efficiently, right? We're just doing DFS, and then that's one nice consequences of DFS is every time you have this edge, that's like, like you're on this, you're on this path, right? And you're pointing back to something that on this path, then that's going to be a cycle, okay? So that's one of the applications of DFS, is to find loops in the graph, okay? And we'll, I'll come back to this point in a bit. But okay, so how long does DFS take? right? So when we did this, right, we only visited every edge at most once, right? Like some edges were, edges were nice and useful, right? These edges helped us make progress. This edge helped us make progress, but this edge was kind of useless, right? It was pointing to something that we've already visited. But in general, right, we were only visiting every edge a constant number of times, okay? So that means the running time of DFS is also O of m plus n, okay? And this plus n is just for, let's say, right, if there are some, isolated nodes here, maybe we'll go there and check that they're isolated, okay? But okay, so the running time is the same as BFS, is O of m plus n, okay? Does that make sense? Essentially, we're like walking on the graph, right? But instead, we're going very deep on one path, and then we come back, and then we go deep on the other path, and then we come back, and then we go deep in this one path, and then we come back, right? So every edge we only visit twice, okay? One time to go down the edge, and potentially another time to go back on the edge when we're backtracking, okay? Okay, so is that okay? M plus n. Okay, so all right. Yeah, and then another way to say it is right in this in the DFS, in the slide with how DFS is described, right? The way it's written is you say, okay, you call DFS on every vertex at most once, or at least, sorry, exactly one time, right? It's first you call DFS on A, and then you go to the neighbor. Then you call DFS on B, and go on and so on, okay? All right, so the running time is O of m plus n. All right. So this back edge is important. So that's one of the nice applications is finding cycles in the graph. Okay. So the main claim is that, okay, so G has a cycle if and only if DFS has a back edge, okay? Okay, and the main thing is, right, for DFS, it doesn't really matter what the, in BFS, it was really important what the starting vertex is, right? Because you're finding distances from that starting vertex to everything else. In DFS, it doesn't really matter. The starting vertex has no special meaning. So it doesn't you can start DFS from any vertex, while it runs. If it finds this back edge, right? You're on this execution path, right? And suddenly you say, okay, there is an edge pointing back to the path that I just came from. That's a back edge. Okay, and that just means there is a cycle in the graph, okay? So to prove this claim, we have to do it on two sides, right? One way is okay, so the first direction is if there is a back edge, then this implies cycle, okay? And that's kind of obvious from the drawing, right? What is a back edge? Essentially, it's right? It's an edge that points to something whose sort of execution path that you're on, okay? So obviously this is a cycle, but the more interesting claim is if G has cycle, then at some point you'll have a back edge, okay? So that's the, so I'm saying no matter how you run DFS, if your graph has a cycle, at some point you'll be in this, in this case where you're at a vertex, you go to the neighbor, you go to the neighbor, you go to the neighbor, and then it's going to point back to you. Okay? At some point, this behavior will happen. Okay? All right, so the first part is easy. The second part is more interesting. Okay, so, right. But it's just like proof by drawing, okay? So now let me draw, let's say the graph has the following cycle, okay? So it like goes from here, here, this is somewhere in the graph, okay? Essentially the main idea is you say, okay, which node in this cycle is the first node that was hit by DFS, okay? I don't know which one it is, but some point, right, some node will be hit. So let's say it's, it's this node. This is the first one, right? Well then, right, then at some, right, it's going to go to the neighbor. And then, right, the neighbor might go some other way. But right before it comes back to this vertex, right, it's going to go to this neighbor. And then this may go somewhere else, but, it's going to, at some point, right, it's going to come back and go to this neighbor. And then it's going to go, who knows where this is going, blah, blah, blah. It's going to go somewhere else. But, right, at some point, it's not going to have anywhere to backtrack to. And then it's going to come here, right? And that point, and at that point, this will be a back edge, okay? Essentially, all this is saying is, like, your neighbors will finish in DFS. Okay, so yeah, so this is an important principle, okay? So your neighbors will finish searching, right, before you, okay? Before you, okay? Right, and that makes sense, right? Like the way DFS works, right? Like I'm going here, I'm going here, I'm going here, sorry. And then I, once I've explored all this, right, this path, then I go one step forward, right? And I explore all this path. Then I explore one, then I go backtrack, and then I go explore this path, right? And who knows? So essentially, like every time I call DFS, right, the way DFS is running is, I call DFS for this vertex, then the neighbor and the neighbor and neighbor. Your neighbors will finish way before you finish, okay? And that's essentially why, you'll find a loop. Essentially, right, you start at this vertex, you go to this neighbor. Who knows what's going to happen, right? Neighbor might go this, this direction. But at some point, right, it has to visit this neighbor before it comes back to you. And then, who knows where this neighbor is going, but at some point it's going to come here. And then at some point it's going here, and that exactly is this back edge, okay? But essentially, right, it's like, you will finish DFS on the neighbors, right? Like, so, before we finish, before finish DFS here, right, we must finish DFS here, okay? That's right. I'll show you the, I'll show you what the code looks like. But you'll see, right, like, we're at a node, we call the other node, and then when we're finished, then we're allowed to go to the other neighbors of the node, okay? Because I'm going to go deep, right? I'm going to explore all this way here, and then when I can no longer explore, then I go back up one, okay? But yeah, I mean, if this proof was a little bit confusing, just go home and read it. But kind of the main high level take point is like DFS. One application of DFS, it helps you find loops, okay? Essentially, like you don't have to do anything, just run DFS and just like keep track of, if you ever find an edge pointing to something that you're on the sort of the execution trace of, then that's a loop, okay? Okay, comments, questions? Yeah, so let's just do like a simple example, right? Let's just say your graph was a loop, okay? Right? Right, then you start from this vertex, then you go deep, right? And at some point you say, okay, you come back here, you check this edge. Oh, that's a back edge, right? Because I'm on the path, right? I haven't finished this vertex yet, but I'm pointing to this vertex. So that means, right, there's a path like this. Okay? Okay. Any comments, questions? Yeah. Okay, so that's one main application of DFS. So let me summarize that. Okay. Okay, so one of the nice use cases is DFS will essentially check if your graph has a cycle, okay? All right? And if your graph doesn't have a cycle, then you'll never hit a back edge, okay? So essentially, it's going to check. Another way to say it is check if your graph G is the directed acyclic graph, okay? And essentially, right, that's why, right, why is this important, right? I mean, one application is in the dynamic programming, right? Like you need to check your dependency graph, does it have any loops? So one way to do that is actually you run BFS, and then it'll check. Okay. Now let's see another nice application of DFS. Okay. Yeah. So another application is so another application is something called job scheduling. And it's also called something called topological sort. Okay. So at a high level, this problem is very natural, right? Let's say that you're writing some code, right? And at some point you need to call the library, and maybe that library calls another library. Like you want to check that libraries are not calling each other in a loop, okay? Another way to say it is, let's say you have you have this very complicated task, okay, that you want to do, and this complicated task is divided into many subtasks, okay, and you need to say, okay, how do I in which order do I do the tasks, okay? So let me give you an example. Okay. Give me a second. F, D, E, and then I. Okay. So let's say you want to solve a huge problem, or you're writing a giant, piece of code, and you've said, okay, I need to solve this, 10 different tasks first, okay? And this is how the tasks relate to each other, okay? Make sure I do the ordering, okay. And essentially, what this is saying is G depends on H, okay? So, if I'm finishing task G, then it must be that I have finished task H before, okay? So maybe these are different codes that you're calling, right? I can't really I can't finish writing the code for G unless I have this task done, okay? So essentially, right, that's why it's called job scheduling. And let's say I have this let me call it dependency graph. Okay, dependency graph. Okay, so the problem is the following, right? I give you this graph of, how different jobs relate to each other, and you go to say, okay, in which order do I do the jobs? Okay, in a way that I'm never doing a job until I've finished all the jobs that I need to be finished first. Okay. Does that problem make sense? Right. And another thing is, right, if somehow, right, if the jobs have a loop, then that means that you can never finish this task, right? So that's also another part of the problem, also check if there are any loops. So that's why DFS kind of seems like it's useful here, right? Because at least, right, if you run DFS, it will check whether there's a loop, right? So for instance, if somehow there's this loop here, then you could never finish anything because all these things rely on each other, okay? Okay. Yeah, so the question is, in which order do we complete the task, okay? Yeah. Yeah. I mean, another way to say it is, let's say you're like baking a cake, right? And one of the steps might be like, oh, put the topping, on the cake, like the cream filling on the cake. Well, like you can't do that until you bake like the cake itself, right? That should be the last step, right? One of the steps might be like, cut the cake in half. Well, you can't do that until, until you've done some other things, right? Or one thing might be like, okay, put the cake in the oven, but you can't do that until you turn on the oven, right? So yeah, so that's like one way to model this, right? You have a bunch of tasks, and they all rely on each other, and the problem is like, in which order do I complete it? So this is the other thing that DFS is really good at. Okay, so any idea about how to solve this problem? Yeah. Yeah.
I guess you focus on the things that have the most dependencies. So like F has 2 dependencies, C and E is more than A depends on nothing. So that's last.
Okay, so that's one idea, but it turns out there's something very simple that we can do. So the algorithm is essentially the following. Okay, what we do is we run DFS, okay, on any node, let's say from G, and then we say, okay, what are the times that the vertices finish, right? And then what we do is we just take, I guess we do the tasks in order of the DFS finishing times, okay? Okay. All right. So let's just see how this goes, okay? So let's say I run DFS, right? So what is DFS going to do? I'm not finished with this node, right? I call the neighbor. I call the neighbor. I call the neighbor. I call the neighbor. Then there's nowhere to go, right? So this node is done, okay? And then I backtrack, right? There's nowhere to go. So this node is done. And then I backtrack, right? There's nowhere to go. This node is done. And then I wait, there's, sorry, yeah, and then there's nowhere to go. This node is done. 5, and then and then I do the other version of DFS, right, where I visit all the nodes. So let's say I visit this node, okay, it'll be 6, Then I visit this node, right? Then I'll finish this is 7. Then I'll do 8, and then last 9, okay? So essentially, right, what we're going to do is just pick a node, do DFS, and we say, okay, in which order did the vertices finish, okay? So like, right, I went deep here. I couldn't do anything, so I finished here. And then I went backtrack. I finished here. And then what you'll notice is that if a vertex is pointing to another vertex, that vertex will finish first, okay? So that means we're going to do that job first. Yeah. Yeah, so in the DFS, right, we'll just check. We'll have this thing where we have to say, okay, has every node been visited? And if it hasn't, then we just go. We start DFS there. Yeah. Yeah, it's like I'm going to start a DFS, and then essentially I'm going to keep track of when things finish. Right, so I started DFS here, right? It hasn't finished because it is going to a neighbor, going to a neighbor, going to a neighbor, going to a neighbor. The neighbor has nowhere to go, right? So then that neighbor is done, right? I went deep. And then, right, I have to backtrack. Well, this has nowhere else to go. So now this is done. Backtrack. This has nowhere else to go. Now this is done. Backtrack. Nowhere else to go. This is done. Backtrack. Nowhere else to go. This is done. And then, right, there's other parts of the graph that I haven't explored. So let's say I go here. Well, I still have something to do, right? I have to go to my neighbor. Neighbor has nowhere to go, so it finishes. Then I have nowhere to go, then I finish, and so on, okay? Yeah, actually, let me show you the DFS code again. Then it'll be a little bit more clear. Yeah, so what is happening, right? Right, essentially it's like saying, yeah, so, right, so it's saying, okay, I start at some node, I go to all my neighbors, and then I recursively call DFS on all the neighbors itself, right? So like, you know, I'm in this deep like recursive call, okay? I'm in the, right, just think of the top part. The second part is just saying visit all the nodes at some point. Just think of the top part, right? So I'm saying, right, I start at some vertex. I look at all the neighbors of that vertex. If that vertex hasn't been finished, right, I haven't finished that, then I just call the algorithm itself on the neighbors, okay? So it's like, right, I'm at some vertex S, right? S has not finished, right? Because it started this like recursive call for all its neighbors, for its neighbor, right? That has not finished because it started a recursive call for its neighbor and so on. So that's why DFS is going super deep. And then when all, you know, when I'm at some node, I'm done. I have no neighbor to go to. Then I'm done. Then I go back up one level, right? And then let's say, okay, for that node, then I go deep on another path and so on, okay? Yeah, maybe, yeah, I guess I'll just leave it here. But essentially, right, the reason it solves this like job scheduling problem is you're never finished until your neighbor is finished, okay? So what that means is if we just look at the DFS finishing times, or like which nodes finish, right, it's always going to be the case that if I point to something, that something is going to finish first, right? Why is that, right? Like, how could I have finished in DFS? Well, I must go to my neighbor first, right? And let that finish, and then I backtrack up, okay? Okay. So, right, so another like conclusion is like, okay, DFS, if you just keep track of like the order in which nodes finish, that will tell you, that will give you a way to order the nodes, right? So initially the input is a graph, right? There's no ordering of the nodes. But if I just run DFS and I keep track of the order in which vertices finish, it lets me order the nodes in a way such that a vertex is, you know, another way to say is a vertex is only after everything it depends on, okay? So that's called a topological sort as a fancy name. But all it's saying is if I give you a directed acyclic graph, it lets me order the nodes in a way that a node is, you know, a node is after all the nodes that it depends on, okay? And how you do that is we just run DFS and just wait until some things finish, and then like the order in which vertices finish is the ordering. And right, another thing is, right, this ordering is not unique, okay? But it's going to satisfy the property that, right, if I depend on something, they'll be done before I need to be done, okay? So, you know, one way, right, if you have this like really complicated dependency graph in your dynamic programming, you run DFS, and DFS will tell you the order in which how to solve those subproblems, okay? All right, yeah, let me go back up here. So let me quickly prove why this works, right? Just run DFS and then just order the nodes in terms of the finishing times. So why does that work for this job scheduling problem, right? So let me say that again, right? Let's say I'm at some job U, right? So like, you know, job U says mix the egg with the milk, right? And what this needs, right, it needs me to like buy milk first, right? So how do I know that, right, v has an earlier time than u? Well, imagine DFS, right? Anytime it, okay, so it can, there's two cases, right? Either it just hits v first without ever going to u. Then, of course, v will finish, and then later on, I'll start DFS at u. But the more common case is, right, I go to u first, right, in DFS. Either v is already done, in which case I'm happy, or I go to v first, right? What does DFS say, right? I visit all the neighbors that have not been finished, okay? Right, so just to say it again, right, like I'm doing DFS, right? At some point, right, I go to vertex u, right? I start DFS at vertex u, right? Why would, then the bad thing would be if u is finished before I ever get to v. But the way DFS works is, right, is like say, okay, I look at all the vertices, all the neighbors that are not finished, I go to them, and I finish them first, right? I run DFS on them first. So of course v will finish because, right, if I imagine like the recursive calls, right, there's like some call for DFS of u, and inside it there's a call for DFS of v, right? So this will have to be finished before this finishes, okay? Yeah, I mean, just like, what was the DFS code, right? It said, right, essentially it said the following, right? I say, okay, I want to run DFS at some vertex u, right? Inside it, right, it was, right, oh, do DFS at v first, right? So of course that will finish, and then I can finish, okay? Questions, comments? Okay, so right, so those are the two main things about DFS, right? One thing is, it'll help you find any loops in the graph, right? So that's also good for this job scheduling problem, because there's loops, right? Then you have to say, okay, you cannot complete this task. Or, right, if the graph is directed, the acyclic graph, meaning it has no loops, right? Then it will give you a way to do the jobs so that you only do something after all the things you need are finished, okay? Right, so that's the two main use cases of DFS, right? In contrast with BFS, right? BFS is solving a completely different problem. It's solving the shortest path problem, right? So DFS has nothing to do with shortest paths, but in some ways, like, it is really useful, right? It's like, I give you this graph. It's helping me, put the vertices in order, so that my place is after all the things I need. Okay. All right. Questions, comments, and you can say, right, both of these algorithms run in O of m plus n time. Okay. Okay. Questions. Yeah. Sorry? N and M? Well, where are N and M? Yeah. Okay, so, right, N is the number of vertices, number of nodes. M is number of edges. So I'm saying the running time is essentially number of vertices plus edges, because it's sort of touching every edge and vertex at most 2 times or something. Okay? Both of these algorithms. Okay, yeah, so if you don't understand the difference between BFS and DFS, like, now is a good time to ask. These are really like fundamental building blocks for more complicated graph algorithms. But yeah, at the heart of it, right, they're just helping you explore the graph in 2 different ways. Okay? One is being very, like, layer by layer. The other is being very deep. And they both have their own applications. Okay? All right, if there are no questions, then I'll see you on Thursday.
I have a question about the second problem in the exam. So
Okay.
there is, in a again, it says it could be solved in an ON table, but I solve it in an ON squared table. Would that be fine?
It depends. If it's correct, then it'll be somewhat fine, but you probably won't get the full points.
Okay, yeah, because I was trying to solve that one like using two index of
Oh,
like,
I see.
ing, yeah.
I see.
And
Yeah, you only need one index. So essentially, the idea is you say, okay, dp of 1 through I is for that string, and you
Yeah.
say, okay, how do I answer? Well, you check all the previous, like, basically, it's very dp of I is 1 plus dp of j,
yeah.
but only for all the j's where like xj up to xi
It's
is a palindrome. Yeah.
Yeah, I think for this one they have to also keep like a 2D array to test whether this is palindrome.
No, you just have to go back and forth, right?
So basically I just do this step inside. my
Oh,
2D
I see.
array.
I
Yeah,
see.
So I just
I
like
see.
the base case I just initialize it.
Well, yeah, I'm not grading it the TA,
Okay.
so we'll have to pray that he's, or we'll have to hope that he's a generous guy.
Yeah.